This is the second module on gas vapor mixtures and psychrometry. In the previous lecture, we had looked at what is air or moist air, its components being dry air and water vapor, and then we looked at how to quantify the properties of that, and we came across three terms, which was absolute humidity, specific humidity and humidity ratio. Now, to proceed further, we need to look at an important concept, which is what is the maximum amount of moisture that air can hold for a given temperature. This is to say that when does air become saturated? So, that is the question. We know from common experience that if we keep putting moisture into the air, at some point the air cannot hold on to that vapor. That vapor becomes liquid or a solid. If it becomes liquid, it precipitates out as a fog or a mist or as rain. If it gets cold enough that it precipitates out, it becomes ice and then goes into snow and all that. So, these are the type of phenomena one sees in the atmosphere, but even otherwise we see that in daily life in many cases. For example, you are in a closed room or a car or a bus and it's cold outside, then we soon start seeing fogging happening on the glass, which is telling you that inside the air is not able to hold on to any more moisture. As soon as it sees the cold surface, it is precipitating out. So, we say that maximum amount of moisture that air can handle or hold is that if it is cooled isobarically, that means you have this saturated air and at constant pressure we cool it, then if immediately water condenses, then we say that that air is saturated. So, that is called saturated air, which means that at that point the partial pressure of water vapor is equal to the saturation pressure at that particular temperature. So, this is the condition at which we can have saturated air. Now, remember that what we have defined now as saturated air has a very different meaning from what we have used so far in thermodynamics, which was a saturated state. This could be a saturated vapor, a saturated liquid or a saturated solid, but all of those definitions were always in the context of a pure substance. We are now looking at a new idea as to say how can you saturate a mixture, which is what saturated air actually means. So, earlier relations that we had derived for relative humidity, we now know that the vapor pressure is equal to the saturation pressure at that temperature. So, it is P sat at the ambient temperature at the air temperature or P A minus P sat at T A. So, which means that if the pressure is known P A and the temperature is known T A, then everything on the right side of this equation is known, and then we can say that from these two we can calculate omega that would be there if the air were to be saturated. So, this is something that comes out of this equation. And if we want to know how much is the mass, then we can say that mass of saturated air using the ideal gas equation of state. That is what we have done here. mass of water vapor for saturated air is the saturation is the pressure partial pressure of water, which in this case is the saturation pressure at T A multiplied by the volume upon the gas constant for water vapor divided by T A. So, again, so now what happens is, as far as this part goes, or if we can even say that what the specific volume in that case, then we get P sat at T A divided by R W V up into T A. So, now in this equation there is only one variable T A. So, once you say that this is the air temperature, then we can say what is the specific volume of air that will be there in the saturated state. So, that is one part. This is an important concept, what is saturated air, and we will now start using it in defining more terms. Before we do that, let us see what the property diagram tells us. So, here I have drawn a T V diagram instead of the usual T S diagram, and shown here is this is the saturation dome, this line is the saturated vapor line, and lines of constant pressure on this will be these lines here. So, let us take a state here and say, well, if this is the state, at that state we come back here and say this state it is T A. We know then that this line is a particular line which will be P W V. So, these are different values of the pressure. So, what we are saying is that the maximum amount of moisture that air at T A can hold will be the case when that vapor is dry saturated. So, if we go say to a state like this or to a state like this at the same temperature, there is no problem. All this moisture the air can hold, because the partial pressure of air, which is P W V, for this is all for a particular P. It can hold this much of partial pressure of water. If we go this direction, we first come to this point, which is also okay in the sense that at this partial pressure, if you cool it, it will go down like this. So, it is not going to precipitate. But if you keep going further down and you come to this point, where now you have dry saturated vapor at T A, any cooling will immediately cause precipitation to take place. So, this is what it will be. This is the what you called just now P sat at T A. So, this is the line which is at this temperature, it represents the saturation line. Specific volumes can be obtained by going down this graph and seeing these values there, or from tables and charts we can do this. Please remember one thing, that these pressures that are being talked of here are partial pressures of water. And although we are looking at the T V diagram, we are looking at the T V diagram for one component of air, where the mass fraction wise it is very small. So, that is why I wrote there that this is at P A, we are looking at all of these things happening. So, if the partial pressure of water vapor increases, P A is constant, it would mean that as you are saturating it, the partial pressure of water vapor at a given temperature T A, this goes up, and partial pressure of dry air will come down. So, this is the type of process that we are looking at from this state, which was state A, say 1, we came down by kept on say adding moisture to the air, at the same time keeping the temperature constant. We could reach up to this point, at which point if we add more moisture, it will precipitate. Okay, so, this is the depiction of the process on a chart. And again, remember that this is for water vapor component of air. There will be a similar chart for air as well. And what intuition tells us that we are looking at the pressure of water is actually the partial pressure of water, which is very small compared to the total pressure of air. So, now we have an idea of what is saturated air, and this gives us a reference point to define some more properties of air. The first and the most frequently used one that we keep coming across all the time is relative humidity, or phi. So, at a given state, which is set ambient T A and pressure P, or we can call that P A, relative humidity is defined as the mass of water vapor in air divided by the mass of water needed to saturate the air at the same T A. So, what you are saying is, this is the system. In this, we had certain amount of air, and in this we already had some amount of water. Then we maintain the same T A at the same pressure and keep adding more moisture to it. The maximum amount of moisture that we can add, that will saturate the air. That is the point where that extra mass that we added, that got added to the original mass of air in this volume, which is the total mass of water that is needed to saturate air for the same temperature. Okay, so, this is not the extra mass of water to be added, but the total mass of water in saturated air, that is what it is. And in both cases, phi is defined as at the same temperature. So, we can now invoke the ideal gas equation of state for water and write these things as P W V into V upon R W V into T divided by P W V saturated at T A times V divided by R W V times T. So, what we have here, we have said mass of water vapor in the air is nothing but mass of water vapor. So, this is W V times the volume of this upon the gas constant for water into T. T is, we can write as T A. In the denominator is the saturated condition, where the pressure becomes the saturation pressure at T A, and that is put here, and we simplify this and we get in the denominator partial pressure of water vapor in the saturated state when air is saturated, in the numerator partial pressure of water vapor. So, phi is the ratio of two pressures. So, this is purely a number without any units, and this is what it means, that what is at this temperature, how much water vapor is there in the air, and what is the maximum amount of water that this particular temperature air can hold. So, we can see on the TS diagram so what we have here are two pressure lines that we saw in the previous picture. This is your constant pressure line, this is another constant pressure line, and the same line also you can plot the constant volume line, and this is our state. And what we are saying here is that what was the mass of water here, which is this pressure in the numerator, this P, and if it were to be saturated, it would go like that. It would come to this state, which is the saturated state at the same temperature, and at this pressure, this is your PWV saturated at TA. So, this pressure divided by this pressure is the relative humidity. So, it is quite different from the other definitions of humidity that we have come across so far, and this is the one which is purely a ratio, and so we can then write this, taking that expression we can write this in terms of omega, which is omega times the ambient pressure upon omega plus 0.622 times the partial pressure of water vapor. Or you can turn around these things and say that the humidity ratio is 0.622 times phi times saturation pressure at TA upon ambient pressure minus specific humidity, sorry, this is a relative humidity multiplied by the saturation pressure at TA. So, what this thing is telling us all is that there is a one-to-one relation between phi and omega. So, you can calculate any one of them, and using this relation you can calculate the other. So, these are not two independent properties. Next, we know that phi is dimensionless, it is a ratio of two pressures or ratio of two masses, and its value lies between 0 and 1, or typically as we see in reports, it is between 0 and 100%, and this is one of the indicators of comfort. So, if you are looking at thermal comfort, it has largely been defined in terms of dBT and relative humidity. Some people call it RH, or we can also call it phi. And everybody has decided that in an air conditioned room there is a range of dBT and RH combinations. So, its dBT would be say 25 degrees Celsius plus minus 1 or 2 degrees Celsius, relative humidity would be say 50% plus minus 10%. So, you would say that this is the ideal comfort condition, where we have said that the air velocity in that particular space is very small, less than like 0.1 meter per second. Clearly, we see our daily experience that it is quite different, in that we often use ceiling fans, where the air, or even desert coolers which give out air at a large velocity, there the velocities go up to like 2.5 meters per second, in which case thermal comfort becomes a function of this and the air velocity. So, this is the case when air velocity is very, very small, and that is what the ideal case is supposed to be. Next, we look at the enthalpy of air. We already had a relation for enthalpy of dry air, we had an enthalpy of water vapor relation. Now, we ask the question, using those two, is it possible to calculate the enthalpy of air or the moist air? So, we have that for two component system, the extensive property of enthalpy is mass of each component multiplied by its specific enthalpy. So, this is for dry air plus m for water vapor multiplied by specific enthalpy of water vapor. How to get these two? We already got expressions for that, and this we know that this can be related to humidity, various types of humidities, and then from there we can get this. Now, to make it into a specific enthalpy, there are two things which could be possible. If we divide throughout by the mixture mass, which is m A, then H A becomes small h a, m d A becomes mass of dry air or mass of air, which is the mass fraction of dry air times specific enthalpy of dry air, and similarly for this one it becomes y w v times h w v. So, this is now enthalpy of air per kg of air. Air means moist air. But we would like to know what is specific enthalpy per kg of dry air. So, for that what we do is we divide both sides by mass of dry air. So, you get H A by m dA is equal to H dA plus this is m water vapor upon mass of dry air into H W V, which gives us that H now referenced on dry air is H A plus omega H W V. So, this is an important relation that we have got, and the units here of H is not just that we are saying it is kilojoules per kg, but it is kilojoules per kg of dry air. And recall how we are going to get H, sorry, this is H d A here. And H W V, which is the water vapor enthalpy, this is, as we have just argued few minutes back, this is H g at T A. So, this is another important relation that will be used in problem solving. It is this property which is listed in the psychrometric chart and in the tables, for the same reason that in many applications dry air mass remains constant, whereas the mass of moisture mass keeps going up and down. Okay. So, we have H reference per kg of dry air. It is important to remember this part. Now that we have a definition of what is saturated air, we will define yet another thing, which is the dew point, or T with a subscript dP. So, what is dew point? Yes, when air is cooled isobarically, that means at constant pressure, the temperature at which water begins to condense is called the dew point. So, it is on the, this is a TV diagram. So, let us see what we see on that. So, on this we have a given state which is put here. It is at this pressure here. This is P, PPA, whichever way you want to call it. The temperature at this state comes here. This is TA, and we are looking at the properties of water. So, what we are saying is that this is the state that we had, and we are saying when air is cooled isobarically, that means if you go this way, it is heated isobarically. These states, it is cooling isobarically. So, this is what we are interested in, that if we keep cooling it, we will reach this point where any further cooling will cause precipitation. So, this is the limiting point, and this is what we can then say that this point, the temperature corresponding to this point is T dew point. So, what this graph tells us also is that dew point is nothing but the saturation temperature at this pressure. That is what this point is. This is the dry saturated vapor line. So, TdP is for water vapor the saturation temperature at the partial pressure of water vapor. So, you can say this is P, or you can call this PWV. So, as long as the partial pressure of water vapor is this, whether the dry bulb temperature is there or here, the dew point does not change, it is the same. It is only when the partial pressure of water vapor goes up or goes down that the dew point will change. So, what happens if you do cooling beyond this point? So, you have a system where you kept cooling it at constant pressure, it became a air got saturated at this temperature. More cooling, air cannot hold any more moisture. Some of the moisture condenses and falls out if the temperature is above 0 degrees Celsius, and the new state that it gets will now start going here, which would mean that some of the water vapor in the mixture got out as liquid. To have equilibrium, you cannot have a subcooled liquid in thermodynamic equilibrium with a saturated vapor. So, what would happen is that because some of the water has gone out, the partial pressure of air will decrease, it will come here, and this will be the new condition. And if you go down all the way, say this is 0 degrees Celsius, and if you cool any further than this, then this moisture will not go to the liquid phase, but will start precipitating out as a ice. And clearly, what you are seeing here is that the partial pressure of water in the air is continuously decreasing as you are cooling it. The total pressure is still the same, which means that the partial pressure of air, the dry air, keeps going up. So, all of this is happening when your isobaric process is there. That means P A is constant, or just P if you want to call it. So, this is what is happening. If you heat it, there is no issue, there is no chance of precipitation, it will just keep going up that line. So, now we got yet one more property for a mixture, which is the dew point. So, now let us see what happens, how we can show these things on a property diagram. The difference here compared to what was there in pure substances is that the property diagram here cannot be one diagram. We have two components with two very different properties, but the processes going on is the same. If initial pressure and temperature was something and the final pressure and temperature is something, we know that the whole mixture has gone through that change. So, we make one property diagram for dry air and another for water. So, this is the T s diagram for air, here is the T s diagram for water. And in this case, we have drawn here the line of 0 degrees Celsius, this is 0 degrees Celsius. For air or dry air, this is an ideal gas. So, there is no question of showing any saturation lines on this. Water, in the pressures and temperatures that we are looking at, is very close to the dome. So, you have this line as the 0 degree Celsius line, and the states, as we said earlier, that we are studying are belonging in this region over here. This point is of the order of 50 degrees C, some point here of the order of minus 10 degrees C. So, you have this, and this is our region of interest. Same temperatures get mapped onto this diagram. So, you come here to 50 degrees C and minus 10 over here, and you have this line, but now this is these are isobars. So, this could be say isobar for 1 bar, this could be say 0.5 or something like that, and then this is isobar for some other case. So, the air conditions that we are looking at are in this region. So, our points are moving in these two regions simultaneously, and that is what only showing what happens to the water is good enough to understand what happens to water, but it is also important to show it on the dry air plot and say, well, what is happening to air also. And we combine both these, and later on we will see this into what is called the psychrometric chart. Okay, so, this is what we have come for so far. We need some more definitions to be done, but before we get those terms to be defined, we need to have a handle on the conservation equations for gas vapor mixtures. So, that is what we will do now. We had earlier written conservation equations first for a pure substance, for a closed system and then open system. Then we developed and extended those equations for a mixture of gases, and now we will further restrict those things to look at mixture of look at moist air, which is a mixture of dry air plus water vapor. So, the forms are very similar. All we have to do is make some substitutions to make sure that we are using the right terms for the mass and the right terms for the properties of that mass. So, here we have a closed system for which a conservation of mass is MCM is equal to constant, which also means that within that system the mass of dry air will remain the same. So, mass of this in the control mass is mass of air, but then it also tells us that since it is closed, mass of dry air in state 1 is equal to mass of dry air in state 2, and similarly mass of water vapor in state 1 is equal to mass of water vapor in state 2. So, that is the conservation of mass. And now we look at the first law, where everything remains same except that E 2 minus E 1 term which was there for a pure substance. We now qualify that E of A 2 A 1, where A is the mixture. And if kinetic and potential energy changes are 0, then we can say that the heat transfer during the process is internal energy of the air at state 2, internal energy of the air at state 1, which here becomes mass of air at state 2 multiplied by specific internal energy of air at state 2. So, air is now the mixture. And how to get U? So far we have only looked at specific enthalpy, is that in each case we will have to go back and use the definition U is equal to H minus PV, and H, for H we had relations in terms of temperatures. Okay. So, that is what we will have to apply when we are looking at mixture air water mixtures in a closed system. And now the second law, it said that S 2 minus S 1 is greater than or equal to the integral from T 1 to T 2 of delta Q by T. Now, S becomes S of A, which is air, minus S A at 1 greater than or equal to the same integral. So, that is the second law applied to a closed system. Now, we come to open systems and say what happens here. Conservation of mass, we have to add the extra subscript to say that mass flow rate at every outflow or inflow is mass flow rate of air. So, m dot A at E is every outflow and I is every inflow. So, air outflow rates minus air inflow rates plus rate of storage of air in the control volume is 0. But remember, air has got two components now. So, we could write a conservation equation for dry air, which says that mass flow rate of dry air at each exit minus the same thing done at the inlet plus d by dt of m dA of the control volume is equal to 0. And we can write a similar equation for water vapor, and all you have to do is in all these dAs that we have written here, we just substitute those by WV. So, when you talk of conservation of mass, in the pure substance it was only one equation. Here, as we looked at mixtures, it is a number of components plus 1, that is the number of conservation equation for mass, and that is what we have here, a conservation equation for air, conservation equation for dry air, and a conservation equation for water vapor, and all three have to be simultaneously satisfied. In steady state, this terms will become 0 and life will become a bit simple. So, this and this in steady state, these terms will be 0. So, there is a little extra complication coming in when we look at the conservation of mass for an open system. At every inflow, we have mass flow rate of air, it will be mass flow rate of dry air plus mass flow rate of water vapor. So, if we take out MD dry air mass flow rate out, it becomes 1 plus the ratio of these two mass flow rates, which is mass flow rate of dry air at the inlet in bracket 1 plus omega at the inlet condition. So, this was mass of water vapor divided per mass of dry air, and the flow rate definition remains the same. So, this became omega at the inlet state. So, this is important to get, because now we are able to express it in terms of the dry air mass flow rate. Okay. Similarly, for every outflow, we can express the mass flow rate of air at every outflow as mass flow rate of dry air at that outflow into 1 plus omega at the same condition. So, these are two equations which will become handy when we solve problems. We then look at conservation of energy, or the first law. So, now this expression is exactly same as it was before, and we are going to write it for steady state. And delta K equal to delta P equal to 0. And so, when you do this, in the terms which was in the brackets, we are ignoring kinetic and potential energy changes. So, what would have been here is m dot A and H A. We can break that up and write in terms of m dot d A at every inlet, H d A at every inlet, plus m dot water vapor at that same inlet, H water vapor at that inlet, and equate it to a similar summation for the exit side plus work transfer across the control volume. So, this expression we can get m dot d A out and write this as H dot d A 1 plus omega I H W V I, and you get a similar expression on the other side, which is for every exit flow rate, the same thing, where I gets replaced by E plus the work transfer rate. So, steady state delta K E delta P equal to 0, almost all the problems we will look at, we will assume that this is the case, and the equation to be used then becomes this one. Otherwise, we have the full equation there plus an unsteady term that would come if the steady state were not there. The second law equation becomes, we just substitute that with every inflow for air, m dot, this should be m dot A at every inlet into S with the specific entropy of air at every inlet. This is m dot A at exit into multiplied by specific entropy of A at each exit, plus summation of Q dot Cv upon T plus rate of generation of entropy is equal to rate of storage or depletion of air entropy in the control volume. So, basic equation is still the same, we are just putting properties for mass flow rate and the properties of the substance with those of moist air. We will now look at the last thing, which is what is called an adiabatic saturation process, because that leads us to the definition of one very important term, and that is where we will then stop. So, what we are looking at is what is an adiabatic saturation process, and say, well, one way to do that is to have a chamber into which you have inflow of air at T1 and phi 1 relative humidity, and comes out at state 2 where temperature is T2 and humidity phi 2. But we also do another thing, which is to make it flow over a bed of water which is continuously being filled from here. So, this is water coming in at state 3, temperature T3. A device like this, and this whole thing is insulated. So, we say that all of this is insulated. So, this is adiabatic. That means there is no heat transfer to anything here. Now, we know from experience, like a device like a desert cooler, that what we are doing is, if we keep running this for a sufficiently long period of time, the temperature will keep decreasing, the air will keep getting more and more humid as it comes out. Then there will be a time where, if we are able to control two things, which is control the flow rate here and to control T3, and this is very long and for a long time, then we can say that this air is completely saturated. So, it is T2 and phi 2, with phi 2 becoming 1. And we further restrict by saying that the water that is being put here at T3, we are able to control the temperature, and say we will be now putting water at temperature T2. So, now what has happened is that this whole system, this is completely insulated, there is no heat transfer. So, Q dot C V is equal to 0, but before that let us define the control volume. So, we will say that the control volume is here, so that is the control volume. There is one inflow here, one outflow here, and one inflow here. So, at this point, and for this control volume, not only is adiabatic, but also there is no work transfer taking place. W dot C V is also 0. So, under this condition, and we kept this as T2, and outcoming air finally reaches the same temperature and gets completely saturated at temperature T2. So, this is what we have done. We have done that through an adiabatic process. We have saturated the incoming air where phi 1 could be less than 1, but now we are getting temperature has gone down to T2 and relative humidity is 1. So, now we apply the conservation of energy and the conservation of mass to this system. We have 3 state points, 1, 2 and 3. M dot at 1 is M dot A at 1, which is mass flow rates of dry air and water vapor. At 2 it is only air, and we can write a similar equation like this, which will be M dot d A at 2 plus M dot W V at 2, and M dot 3 is equal to W 3, which is nothing but the evaporation rate. So, what is happening in this is that there is water vapor evaporating into it, and it is cooling this thing down because it has there is the HFG involved in it. At the same time, there is heat transfer taking place from T1 to this, because T1 is greater than T2 or T3, there is sensible heat transfer H, heat transfer coefficient to this. But as a whole, this system is perfectly insulated. Now, because the mass flow rate of dry air has not changed from inlet to outlet, we can say that m dot dA 1 is equal to m dot dA 2, and so mass flow rate of due to evaporation, which is 3, is m dot dA 1, or it could be m dot dA 2 multiplied by omega 2 minus omega 1. Omega 2, and these are the moisture contents of the air. So, these are absolute numbers, this is not a fraction. We now apply the conservation of energy with already having said that Q dot Cv and W dot Cv are 0. And then we apply the first law, m dot A inlet into H A inlet is similarly, we can write this expression for the outlet condition, m dot A E times H A E. And when we simplify this, we get m dot A at 1, H A at 1 plus m dot 3, H A at 3. This is equal to m dot A of the outflow multiplied by specific enthalpy of air at that condition. Now, what has happened is that this thing is what we were putting in, and we are putting it at T3, which is in the long run equal to T2, which is the saturation temperature of water. So, this is HF at 3, which is HF at T2, or you can call it T3. So, when we simplify this further, we will get the expression that omega 1 into H W 1 minus H F 3 is equal to H D A 2 minus H D A 1 plus omega 2 H W 2 minus H F 3. So, that is the expression we have got, and we will now just do a little bit of simplification on this. And invoking that in steady state, T2 is equal to T3, phi 2 is equal to 1, and we can simplify this and we get two relations. One relation which is omega 1 is Cp 0 dry air multiplied by T2 minus T1 plus omega 2 HFG at temperature 2 divided by HWV1 minus HF3, and omega 2 is equal to phi 0.622 partial pressure of water vapor saturated at T2 divided by PA at 2 minus P water vapor saturated at T2. And this is where we were trying to come, is that now we have T2, which is an important parameter that has come out. This is called adiabatic saturation temperature. Also, this is what is called the thermodynamic wet bulb temperature. That is the importance of this whole exercise, that we have now come across a thing that if we can saturate air in an adiabatic process, then we cool it down to a temperature which is called the wet bulb temperature. So, this is what it is, the thermodynamic wet bulb temperature or the adiabatic saturation temperature, the temperature to which air will be cooled when it is adiabatically saturated with water vapor. And that is what we experience. We have used this, say, in desert coolers or keeping things cool by in earthen pots, water stays cool by evaporation. And we call this the thermodynamic wet bulb temperature, because it is practically slightly different from the wet bulb temperature TWB, which is what we measure in a lab, where we take a sensor and we take this sensor and wrap around it a porous cloth, a fibrous material, all of which is kept in a container which has got water vapor in it, liquid water in it. So, this is all liquid water, and this is what we can call it as a wick or a porous fabric, and this will let it remain in air or blow air slightly over it. As the water evaporates, it generates a saturated condition, and the temperature indicated by this is what we call the wet bulb temperature, or TWB, or often called WBT. This is like if we were to measure the temperature in that experiment that we did, this whole device, this is called an adiabatic saturator. And T2 either can be measured as the dBT of this, or we can measure the temperature of this water. Both are at the same temperature, and that is what will give us what is the thermodynamic wet bulb temperature. So, this is a perfectly an adiabatic process. This is not perfectly adiabatic in the sense that there will be some conduction through the stem, and because air is flowing over it and air temperature is more than this, there will be some heat transfer taking place to this to the bulb. Because of this, the wet bulb temperature that we measure is slightly greater than the thermodynamic wet bulb temperature, but for all practical purposes we use this and say that wet bulb temperature is approximately the same as the thermodynamic wet bulb temperature. So, this is yet another important property that we have come across, and we will conclude by showing it on the TS diagram, where this is the saturation vapor line. This was the pressure at which the air was working. This was our initial state, and what we did was, if we had cooled it at constant pressure, so this is isobar, if we had cooled it like this, we would have reached the dew point. This is the dew point, but in an adiabatic process we went across like that and reached this point, which is the wet bulb temperature. So, that is the difference, and with that we come to the end of this lecture, and we now realize that we have all the necessary tools to tackle practical applications of air water mixtures. So, we defined a whole bunch of properties. Then we came across a new thing, which was the adiabatic saturator, and from there we got the wet bulb temperature, and now we had also put in the process the conservation equations for air water mixture. And so, with all of this, we can now look at applications which will take up a few applications in the next lecture. So, at this point we will conclude this lecture, and thank you.